Okay, so, all right, we are recording. So we were talking last time, well, we talked about section 8.3, where we used integral and comparison tests and also the limit comparison tests to determine the convergence or divergence of infinite series where the terms of the series are all positive. Okay, and that's nice, that's fine. But what if you have a series where the terms are not all positive? What if the terms of the series are positive, negative, positive, negative, positive, negative, and so forth? Well, then you can't use the comparison test directly, so section 8.4 gives us some other tests that we can use for establishing convergence or divergence of infinite series. And the one test that we already learned was the alternating series test. And we used the alternating series test to establish that the series in A, and you can see this is in the last lecture we did in the recording. The series A looks like a harmonic series, but it's not a harmonic series because the terms of the series are alternating. Positive 1, negative a half, positive a third, negative a fourth. It's an alternating series when terms go from positive, negative, and continue that way. So we actually established using the alternating series test that this series converges. This alternating harmonic series converges. So the regular harmonic series, where you add all positive terms, 1 plus a half plus a third plus a fourth, and so forth, that series diverges. But the alternating harmonic series, which is sometimes what this series is called in A, converges. All right, and then we looked at the series in B, where we had another alternating series. But this series diverged because even though the terms of the series are alternating, but the -1 here does not affect the terms of the series as n for when n is large. So essentially, the terms of the series when n is large behave according to -1 to the nth power times 3n divided by 4n. Well, that's -1 to the nth power times 3/4. So the terms of that series, as when n is large, when you're far into the series, the terms of the series start behaving like 3/4 minus 3/4 plus 3/4 minus 3/4, and so forth. And the series just never converges. Okay. So and that's by the test for, and formally we showed that with the test for divergence. So we worked with A and B, but now we're on part C. So part C, your series is n equals 1 to infinity of the cosine of n divided by n squared. And incidentally, we are assuming that n, the angle n, is in radians. We never do these problems when n is, in degrees. Okay. All right. And let me just see here one moment. Okay. So, well, do you think this series in C, do you think it could be possibly an alternating series? I mean, the alternating series test was easy to use. And it's clear that, I mean, okay, so Tina thinks it could be. It's clear that the terms of this series in C are going to get smaller because the numerators are, cosine of 1, cosine of 2, cosine of 3, and then the next term would be cosine of 4, cosine of 5, and so forth. The numerators, the cosine function is bounded between -1 and 1 because of the graph of the cosine function. So you have terms in the numerator that are always between -1 and 1, but the denominators are increasingly getting larger. So the terms of this series in C certainly approach 0. Okay, and you know, that's good. It's not enough to make the series converge, but it's good, right? We need that in order for the series to have a chance of converging. But if we're to try to use the alternating series test, let me go right to the solution here. If we try to use the alternating series test for C, well, you know, we say, okay, well, the cosine of 1 is 0.5403. Okay, the cosine of 1 is 0.5403. The cosine of 2 is -0.4161. And then the cosine of 3 is -0.990. Okay, so this means that the series is not an alternating series, because so we started off okay. The cosine of 1 was positive, cosine of 2 was negative, but the fact that the third term, which has the cosine of 3 in it, you know, third term is cosine of 3 over 3 squared, but the cosine of 3 is negative. So in other words, the terms of the series, the first 3 terms, you have a positive and then a negative, but then a negative after that. And so you don't have an alternating series anymore. And so you cannot apply the alternating series test. Okay? But the thing is, you can't use the comparison test on this series. You know, again, let me see here, one moment. Let me just go back for a minute. Okay, we'll go back to the solution, but you can't use the alternating series test on this series here. But the thing is, the terms of the series are not all positive, so you can't use the comparison test. You can't use the comparison test directly. But what we can do is we can say, well, let me study how this series behaves. What if we were to look at the series where n equals 1 to infinity of absolute value of cosine of n over n squared? In other words, we take the absolute value of the terms. Okay, let's study this series here. And then if we can, incidentally, by putting absolute value around the cosine of n over n squared, it makes all the terms of this new series positive. Okay, so we're going to look at that series, and I'm going to show you why. We're going to use something called absolute convergence. So we're going to consider this series here. And incidentally, for this series, the series where n equals 1 to infinity of the absolute value of cosine of n over n squared, for that series, we know that the terms of the series, which are the absolute value of cosine of n over n squared, those are going to always be less than or equal to 1 over n squared. Okay, so when you look at what I'm doing here, what test do you think I have in mind with this? What I'm just doing here, where I have the inequalities. What test do you think I have in mind? I mean, let's think about, we have 1 over n squared. think about the series, the sum, the series of 1 over n squared. What kind of series is that? Okay, good, Michael. It's a p series. Okay, this is a p series. And so what we're going to do is for this series here, I'm going to look at the p series. I'm going to compare this series here with this p series here. So we know that the sum equals 1 to infinity of 1 over n squared is a convergent p series because p equals 2, that's greater than 1. So that means then that the series n equals 1 to infinity of the absolute value of cosine of n over n squared, that would converge by the comparison test. Okay, that would have to converge by the comparison test. All right, let me know if there's any questions so far. And convergence, by the way, convergence for this series here, okay, series n equals 1 to infinity of the absolute value of cosine of n over n squared. When we say that series converges, what are we saying about the sum? What can you tell me again about the sum if the infinite series converges? What's that mean about it, the sum of the series? The sum is a finite number. That's right, Tina. It's a finite number. Now, we don't know what that number is, and we might need to program a computer, write a computer program with a for loop or a do loop in it for I equals 1 to n, and then let n be a billion or something to get a good idea of what that sum is. But the point is that that series converges. But remember, this is not the series we're interested in, right? We're interested in the series n equals 1 to infinity of the cosine of n over n squared, not where we have the absolute values. But it turns out that this is going to be very helpful, that we establish that this series converges. And let me show you why. We say that our series is absolutely convergent because the sum of the series where you take the absolute value of the terms converges. If that's the case, then our series is called absolutely convergent. And it has to converge also. It has to converge also. Okay. The idea here is if the series n equals 1 to infinity of the absolute value of the terms converges, then the series would certainly converge as well. Let me see if I can maybe make this a little more intuitive for you. I'm going to write down both series here. One moment. Okay, class, so I'm just writing this down. Absolute convergence tends to be for students something that's a little difficult for them, but it doesn't need to be. Okay. Okay, so look at what I have here now. I wrote down series 1 and series 2. Now, series 2, you're adding up a bunch of positive terms. Now, in series 2, converges, which means it has a finite sum. Would series 1, would its sum, would the series in that series 1 here, with just the series, with just the terms cosine of n over n squared, without the absolute values, would series 1 have a smaller sum than series 2? I mean, could we say that series 1 is less than series 2? Michael says yes. Felicity says yes. Well, why can we say that? Why can we say series 1? Why can we say series 1 is less than series 2? That's right, Michael. There are negative numbers in series 1. And the negative numbers will combine with the positive numbers, and it makes things smaller. So the idea is that if series 2 has a finite sum and converges, then certainly series 1 would have to converge also. So that's the idea behind absolute convergence. All right, are there any questions on that? It's used a lot. It's used a lot. Okay. All right. Okay. Oh, Kahindi. Well, oh, I'm sorry. Hold on. I didn't see my chat thing. Hold on. Oh, thank you, Kahindi. If it applies to divergence as well. No, it does not, because series 2 is bigger than series 1. But if series 2 diverges, that doesn't mean that the smaller series is going to diverge. The bigger series might diverge and the smaller series could converge. It only works it works if you have convergence, but not divergence. Okay, very good, very good. All right, all right. Now give me just a moment here. I want to upload another a few more examples here. But are there any questions before we move on? I guess to upload, I'm gonna have to take off this document. Unless, hold on, will it let me share? Oh no, I can do that. Let me just get it here. Okay, I'm uploading it now. So we're going to look at a few more examples here. So just give it a moment here. Okay. Okay, and let's okay, so I'll give you a moment to put this in your notes. Let's look at a few more examples for section 8.4. All right, I'll give you a moment to copy the examples down. Okay, so now let's look at this first series here. One moment. Okay, all right. So students, what is this series here? I mean, I'm looking at the series. You're looking at the series. We can't say it's an alternating series because, to say that's an alternating series, incidentally, this series n equals 1 to infinity of sine of 4n divided by 4 to the nth power, we'd have to show that the series truly alternates. And, at some point, it might alternate for a while from positive, negative, just like the last series we looked at did. But eventually, you're going to get two terms that are both negative or two terms that are both positive. So we can't use the alternating series test. The 4 to the nth power in the denominator, this part of the series, what does it kind of remind you of? What series does that remind you of when you have 4 to the nth power in the denominator? Which, okay, that's right, Michael. It reminds me of a geometric series. So I'm thinking when we do this problem that somehow geometric series is going to be involved. Okay, well, let's go ahead to the solution. Okay, oh, okay. Well, what we're going to do is we're going to work with absolute convergence again. Okay, so I'm going to look at the term, the absolute value of sine of 4n divided by 4 to the nth power. That's less than 1 over 4 to the nth power, which equals 1/4 to the nth power. Okay, and I know that the series n equals 1 to infinity of 1/4 to the nth power is a convergent geometric series because it has a common ratio of 1/4, and that's less than 1. So this problem is going to work similar to the last problem. And by the comparison test, since this series here, our geometric series, converges, that means then that our series, where we have the absolute value of the terms of the series, that converges also because it's a smaller series. And therefore, we can say that our series, the series n equals 1 to infinity of the sine of 4n divided by the 4nth power, our series is the series n equals 1 to infinity of the sine of 4n divided by the 4nth power. Our series converges absolutely and hence converges. Okay, and so like on exam 4, for these kind of problems, I mean, oftentimes in WebAssign, they're multiple choice. Okay, multiple choice, it's either converge or diverge, and all the credit goes on the right answer. But for the exam, normally the multiple choice, I don't require work, but for these kind of problems, I could require work, but I would let you know. So this is the kind of work I would be looking at. Okay, looking to see. Okay, you have to justify that your series converges or diverges, and you have to provide a clear argument, just like this, in order to get credit, right? Right. You have to show me you understand the concepts. So, all right, are there any questions on Series A here before we move on? I think when you do these series, when you do these problems, you have to just kind of take your time and think a little bit. It's not like adding 2 plus 3. Okay, 2 plus 3 is 5. That's easy. Here, you have to just think a little bit. You don't want to click converge or diverge in WebAssign until you've thought it through and tried to justify your feelings as to whether the series converges or diverges. Okay, if we're good with this, if there are no questions, let me go to the second series. Are there any questions? All right. Well, all right, let's take a look here at this series here. Okay, we have the series where n equals 1 to infinity of -1 to the nth power times n cubed over 3 to the nth power. Now, what can we say about this series? What kind of series is the series in B here. Okay, good, Michael, good, Rodrigo. It's certainly an alternating series. Okay, and to use the alternating series test, you know, the -1 to the nth power in there means it's an alternating series. Now, to use the alternating series test, we have to establish that hold on, let me just, it's a little bit tight here. Hold on one moment. Okay, so to use the alternating series test, we have to establish that n cubed over 3 to the nth power, which is the Bn term in the alternating series, we have to establish that the sequence of those terms, you know, n cubed over 3 to the nth power, so that would be like, you know, that would be 1 cubed, sorry, that would be, we're starting at n equals 1, so that would be, let me just write it here, you know, that would be 1 over 1 times 3 to the first. Sorry, it would be 1 cubed over 3 to the first. And then the next term in the series would be 2 cubed over 3 squared. What would the next term in the sequence of terms Bn be? What would the next term be? You can chat it out for me. Let's see, Kahindi says 3 cubed. Almost right, Kahindi. 3 cubed over 3 cubed. And then next you'd have, what would the next term in this sequence be? What would the next one be? 4 cubed over 3 to the 4th. That's right, Rodrigo. One moment. And let me just shut that off. Four cubed over 3 to the 4th.
Just the right size. It's there.
And the sequence just continues. It continues. Now, do you think it would be easy to establish, if we were to use the alternating series test for this, to justify convergence of the series, of this series B, we would have to show that the sequence of terms approach 0. Do you think it's easy to show that this sequence of terms approaches 0? You know, does that sequence approach 0, you know, as n goes to infinity? Would that be easy to show? I mean, is it, put it this way, is it obvious? Is it obvious that this sequence of terms here approaches 0? Yeah, it's not really obvious. That's right, Tina, that's Kahindi. It's not obvious. Okay, remember the sequence could diverge, the series could diverge, right? So but to use the alternating series test to use it to show that the series converges, we would need to show that this sequence of terms, the Bn sequence here, approaches 0, and that's not obvious. So I don't want to use the alternating series test here. It's not easy to apply. Not easy to apply. So what we're going to do is, instead of using the alternating series test, and incidentally, if I were to try to use absolute convergence on this series in B by taking the absolute value of the terms, well, usually when you use absolute convergence, then what you're doing is you're going to apply the you could apply the comparison test. But for me, it's not obvious what terms I would compare the terms to. What series would I compare this to? So really, the using absolute convergence is also perhaps not the best way to go. So what we're going to do is we're going to go in the we're going to go in the ebook here. One moment. Let me just bring up the ebook. Okay, let me get it here. Class. Open the student view. Access the ebook. I'm going to show you a test called the ratio test. We're going to look at a test called the ratio test. Okay, and I'm going to bring it up here. Okay, and so we'll come back to this series. We'll come back. Let me bring up the ebook. Okay. Can everyone see the ratio test on their screen okay? All right, very good, very good. So this ratio test here says the following. Look at the ratio of terms. Okay, so let's look at the first part here of the ratio test. If you were to take the ratio of the n plus first term to the nth term, okay, in other words, take a term in the series and divide it by the previous term in the series. Look at the absolute value of that ratio and let n go to infinity. If the ratio equals L, okay, a number, and that number is less than 1, then we can say our series is absolutely convergent. Okay. Now, when we say ratio equals L less than 1 in part 1 there, what is this? What is, ratio less than 1? What is this? What does this remind you of? What series whose ratio is less than 1, or if a series, if the absolute value of the ratio is less than 1, that series converges. What series does that you've seen? What series does that you've seen? That's right. And Tina, I saw your answer too. I just wanted another few other people to think about it and reply. A geometric series. So a geometric series, when you take the absolute value of the common ratio, if that absolute value of the ratio is less than 1, the geometric series converges. And what we're saying here with the ratio test is study the ratio of the terms of the series. Study the ratio of a term of the series divided by its previous term. If that ratio, as n goes to infinity, equals a number, L, and that's less than 1, then what you're saying is that your series behaves like a convergent geometric series eventually. That's what that means. Okay, that's what this first statement means. Eventually, your terms of the series, eventually your terms of the series will behave like a convergent geometric series. Take a look at the second statement. Take a look at the second statement here. The second statement says, suppose that the ratio of your terms of the series, I'm going to say it more carefully. Suppose you look at the ratio of a term in your series to the previous term in the series. And as n goes to infinity, the absolute value of that ratio equals L. Okay, a common ratio. And that ratio L is greater than 1. Well, then the series will diverge. And that's just like a divergent geometric series, right? If the absolute value of the common ratio is greater than 1, the geometric series diverges. Okay, how many so far are comfortable with the ratio test with the statements 1 and 2? How many are just like comfortable with what it's saying and what it means? Good. Cologne's comfortable. Michael's comfortable. Snega's comfortable. Very good. And again, all you're doing is you're saying, really, with statements 1 and 2, you're saying, hey, my series is behaving like a geometric series, and either the series will converge or diverge based on how the common ratio, based on the common ratio. Now the third statement here says this. Third statement says, if the ratio of the n plus first term to the nth term, in other words, for your series, if the ratio of a term in your series to the previous term, okay, as n goes to infinity, if that ratio equals 1, then the ratio test is inconclusive. In other words, no conclusions can be drawn about convergence or divergence of your series. So what happens is, a lot of times when students see the ratio test, they say, well, gee, this looks pretty easy to use. I don't have to think too much. I'll just apply the ratio test to see if my series converges or diverges. But what often happens is the ratio test, you'll get a 1. You'll get a 1, and so the ratio test is inclusive. That means then that you have to apply one of your other tests that you've learned. Okay, so the ratio test is not a panacea. It's not something that's going to work all the time, but it'll work sometimes. Okay, and they have some comments here. Maybe I'll put them in yellow. They have some comments here, or wait, maybe I'll put them in green actually. They have some comments here below the ratio test, which are consistent with what we've just discussed. Okay, where you're really, if the ratio test, what you're doing is you're trying to establish that your series acts like a geometric series when you go out into the series, when n is large, when eventually your series, the terms of your series will behave like a geometric series. Okay, but of course, if in part 3, if you get this result where the ratio of the n plus first term to the nth term equals 1, then the ratio test is inconclusive. Okay, so like for instance, I think this is worth looking at. Let's say that you have the series, maybe I'll put it in yellow, kind of switch the colors here. Let's say you have the series 1 over n squared. Now that series is a p series, and you know that series converges because p equals 2, which is greater than 1. But if you just want to apply the ratio test, okay, the n plus first term would be 1 over n plus 1 squared. The nth term is 1 over n squared. And the ratio of those terms as n gets large, as n goes to infinity, is 1. So that means that you can't use the ratio test to establish convergence of a p series because the ratio test gives no information. All right, so that's just kind of an example there of where the ratio test fails. Are there any questions on that before we get back to our example? All right. Well, then let me stop the sharing here and go back to our example that we were looking at. Okay, so here's series B. Okay, here's series B again, and what we're going to do is we're going to try the ratio test out for series B. We're going to try to use the ratio test on it since none of our other tests are really going to help us. So I'll go to the solution here. Okay. Like I said, for our series, this series, none of the previous tests we learned can be easily used to establish convergence or divergence of the series. Therefore, we'll try the ratio test. So the ratio test, the nth term is -1 to the nth power times n cubed over 3 to the nth power. Okay, so this is the first step then in the ratio test, is looking at the n plus the absolute value of the n plus first term to the nth term. So again, the ratio test, what we're doing is we're trying to establish absolute convergence of our series, and therefore then our series will converge. That's why we're taking the absolute value. But also it has to do, the ratio, the geometric series, for a series to converge, we look at the absolute value of a common ratio. So really 2 reasons. Okay, so let's see here. Are there any questions on this first part here where we have so to get the n plus first term, you just replace n with n plus 1. Okay, so that's how you get a sub n plus 1 in the numerator. If you take the nth term, okay, like here on the bottom, the nth term is -1 to the nth times n cubed over 3 to the nth power. If you replace all the n's, okay, if you replace all the n's here with n plus 1, then that's going to get you what you have in the numerator. That's your n plus first term. Okay, if there are no questions, what we want to do is we have a fraction divided by a fraction. So I'm going to take then the fraction in the numerator and multiply it by the reciprocal of the fraction in the denominator. And that's what occurs here. Okay, and then what I do is I have to simplify this fraction. So to me, it makes sense to put like terms over like terms. And that's what I've done there. Okay, are there any questions so far? Okay. So then, let's see, Felicity asked, how did I get this last part here? What I did was, so I have in the denominator 3 terms in the denominator, and I also have in the numerator 3 terms here, on this second part. So I just rewrite the product on top of the 3 terms and the product on the bottom of the 3 terms this way. I just rewrite it's sort of like, yeah, it's like if I have 1 times 3 over 5 times 4. Okay, I can write that as 1 over 4. Felicity sees it now, good. I can write that as 1 over 4 times 3 over 5. I mean, I can rearrange, since everything's being multiplied and divided, I can rewrite that. And the reason I do that is, well, I want to simplify things. So -1 to the n plus first divided by -1 to the nth, what would that equal? The bases are the same. What do you do with the exponents? So -1 to the n plus first divided by -1 to the nth. What would that equal? That's right, Michael, -1 to the first power. Subtract the exponents. N plus 1 minus n is 1. What about 3? Let me just clean this. All right, so this here would equal -1 to the first power. What about this part here, the second part? 3 to the nth divided by 3 to the n plus 1. What's that equal to? Bases are the same. Okay. Is that, it's equal to 1/3. One-third. Okay. So if I may, I'll go to the next page and continue. Are we good so far? All right. So then the absolute value of the n plus first term to the nth term, that ratio, is going to equal the absolute value of negative 1 to the first times 1/3 times n plus 1 over n to the third power. Okay, so if I go back here, let me just, this here, n plus 1 cubed over n cubed, can be written as n plus 1 over n to the third power. So we get here, and the absolute value of a negative becomes a positive, and the 1/3, well, I mean, this part here of the expression is positive, so I can drop the absolute values, and you know, n plus 1 over n is the same as n over n plus 1 over n, and that's going to be 1 plus 1 over n to the third power, and that's going to approach, as n goes to infinity, that's going to approach 1 to the third power, because 1 over n goes to 0 as n goes to infinity. So the ratio of the n plus first term to the nth term is going to approach, it's going to approach 1/3 as n goes to infinity. And so by the ratio test, our series is absolutely convergent and hence convergent. Okay, let me Okay, please let me know if you have any questions. Okay, are there any questions? I'll go to the next page and show you just a little bit more on this, but are we good on this page here? Maybe give me a thumbs up if you're good so far. All right, Michael's good. All right, Rodrigo and Snega, very good. Well, so, you know, here's kind of this is just a little note I made. I want you to feel, you know, comfortable with what you're learning. Series, you know, when I started teaching Calculus 2, and you know, my students would tell me that, like, the chapter 8 was the hardest chapter, you know, and I thought to myself, well, the convergence or divergence of series, if I could share some intuition, it would be helpful, and that's what I'm doing. So what this means is that the later terms of this series, the series where n equals 1 to infinity of the absolute value of our term, of the terms, it's going to behave like a convergent geometric series with common ratio 1/3. So eventually then our series, Okay, eventually, I want to be careful. So eventually this series, where we've taken the absolute value of the terms, acts like a convergent geometric series with common ratio of a third. So therefore, if that series converges, then our series, where n equals 1 to infinity, of negative 1 to the nth power times n cubed over 3 to the nth power, our series has to converge as well. I mean, this is what's going on. This is what's going on. But you know, go ahead and copy it down. Let me know if you have any questions on it. Okay. So the ratio test really, you only want to use it. You use it when you have like complicated, like really complicated looking series. Really complicated looking series. That's when you want to use the ratio test. But you don't want to use it just, just to, I mean, what I'm trying to say is if you try to just use it all the time, a lot of times it isn't going to work because you're going to get a ratio of 1. That's right, Michael. Exactly right. Exactly right. You'll spend a lot of time, and you'll end up getting uh, a 1. All right. Are there any questions at all? Okay, what I'd like to do, I do want to give you some time in class to start the section 8.4 assignment that's due on Sunday. There's going to be one due on Sunday and another one due next Tuesday from section 8.4. I don't think we'll have time to cover section 8.5 today, but I want to do another problem with you, section 8.4 problem, that you'll see in the homework. So I'd like to get to that example. And so, are there any questions? May we move on? How many think this is pretty cool what you're learning? I mean, at least, is it making anybody nervous? Are you feeling pretty cool about it? Maybe I'd be curious how you feel. Okay, Tina's nervous, very nervous. Is anybody loving it? All right, Felicity likes it, kinda. Okay. Okay, Snega, I don't know if that doesn't look like a happy face. Alan says cool but confusing. Oh, Snega's mutual. Oh, wow, okay. Tina is a little bit, we're getting some unhappy faces, some sad faces, but then there's some people that are happy. Okay. Well, you know, Rodrigo says it's all right. If you always think intuitively about things, and it'll help. All right, so let's go ahead here and move on to another example here. Now, what I want to do here is talk about something called the alternating series estimation theorem. Okay. So, and we're going to use it to help us estimate the sum of a series. So before, in one moment, We're still in section 8.4. Back in section 8.3, when you learned about like the integral and comparison test, you also learned a theorem called the remainder estimate for the integral test. And you could use the remainder estimate for the integral test to help you find out how many terms of a series you need to add to get within a certain margin of error. Okay, but that worked for series where all the terms were positive, okay, and decreasing and so forth. You know, a convergent series where all the terms were positive. That's what the remainder estimate for the integral test was used in section 8.3. But in section 8.4, we're not working with series whose terms are all positive. Okay, so, but there is, if we have a, or so I should say, how can we estimate a series when the terms of the series are not all positive? Well, if you have a alternating series, you can. So we learned by the alternating series test that if the terms, and you don't need to copy this down unless you want to, but the theorem, alternating series estimation theorem, says if you have a convergent alternating series, and that's what steps one, if you have an alternating series and steps 1 and 2 are satisfied, then that alternating series is going to converge. And that's by the alternating series test you learned in section 8.4. But we can say a little bit more than that. If you wanted to approximate the sum of the series with the nth partial sum, which is the sum of the first n terms of the series, then the remainder, or the error, the remainder using the nth partial sum, which corresponds to the error in your approximation of the series S by the nth partial sum, the error is going to be less than or equal to the n plus first term of the series, and ignoring the plus or minus part. And you're doing that because you're taking the absolute value of the error or the remainder. So this is called the alternating series estimation theorem. And what I did was I said, well, I think a little example would help you feel comfortable with that. So let me show you a little example that reinforces this idea here. So let's say you have the alternating harmonic series. Okay, let's say you have where the series is -1 to the n minus first power. Sorry, the series is -1 to the n minus first power times 1 over n. We already established by the alternating series test that series converges. Okay, so what I've done is, let's say that I'm going to estimate my sum, my series S, with the fourth partial sum, which would be the sum of the first 4 terms. Well, if that's the case, then the error in my estimate would be equal to a fifth, okay, a fifth minus a sixth plus a seventh, and so on. It would be the remaining part of the series. But this R sub 4, okay, this R sub 4 here, which is the sum of the remaining terms of the series, that has to be, if you look at the absolute value of that remainder, it has to be less than a fifth. A fifth is B sub 5. Okay, so, you know, in the alternating series test, the absolute value of the remainder R sub n is less than or equal to B sub n plus 1. Okay, well, I'm saying that the absolute value of my remainder, R sub 4, is less than or equal to 1/5, which is B sub 5. And it's sort of obvious. Hopefully it's obvious to see. I mean, if you take a fifth, like if you have a fifth minus a sixth, that's less than a fifth. If you have a fifth minus a sixth plus a seventh, that's less than a fifth, because you know the seventh is less than the positive seventh is less than negative 1/6. So I mean this part of the series, this remaining part of the series is never going to be more than a fifth. Okay, therefore, if I were to add the first four terms of my series to approximate the sum of my infinite series, I'll be within a fifth. I'll be within a fifth. That approximation will be within a fifth, 1/5. Okay, how many find the example helpful for reinforcing the the statement here? Okay, Michael finds it helpful. Tina, excellent, excellent, excellent. Okay, so that being said, let's go ahead. If there are no questions on that, let's go ahead and look at an example. Okay, are we ready to move forward? Okay, all right, so, okay, we want to estimate the sum of this series correct to 3 decimal places. Let me give you a moment to copy the example down. Okay, so we want to estimate the sum of this series correct to 3 decimal places. And, you know, you've dealt with n factorial before. Okay, so this would be the kind of series that you would use the ratio test for to establish convergence of that series. This series, this alternating series, converges. Okay, and Well, I want to be careful here. I guess, no, you wouldn't need the ratio test for that. You could just use the alternating series test. It's obvious that the terms of the series are decreasing and getting smaller, so that's fine. All right, so what I want to do, I want to show you the solution here from the book. I actually got the solution from the book. And of course, it's obvious that the terms of this series are going to satisfy the alternating series test. And let's see now, they say in the problem that we want to approximate it correct to 3 decimal places. All right, so what they do is they write out some terms of the series. They write out some terms. So here's the series S. They've written out some terms. And I want to make sure you're comfortable. So, you know, like 0 factorial is 1. 1 factorial is 1. 2 factorial is 1 times 2. That's why you have a 2 there. 3 factorial is 1 times 2 times 3, or 3 times 2 times 1. That's why you have a 6. 4 factorial is 4 times 3 times 2 times 1. That's why you have a 24. So they've written out 8 terms of the series. Okay. And you know, how many terms of the series are we going to need to get our estimate to be correct to 3 decimal places? Well, what they comment on is that this term here, I mean, it's negative, but the 1 over 5,040 is b sub 8. Now, in the book, they call that b sub 7. And the reason they do that is because if you notice, terms of the series starts at n equals 0, okay, instead of n equals 1. But I think the book is actually wrong. I don't think they should be calling. I mean, this 1 over 5,040 is the 8th term of the series, so it should be called b sub 8. I don't think it should be called b sub 7, even though you could adapt it to. You could, I guess, do that. I find it confusing. So the 8th term of the series is negative 1 over 5,040, but then just ignoring the negative, b sub 8 is 1 over 5,040. And that is equal, that's less than 1 over 1,000, which is equal to 0.0002, okay? But really, I mean, if you, I want to say this the right way. I mean, the way the book's doing this, well, I mean, I guess what I'm saying is you don't really, this part here is not necessary in my view right now to say this. This is not necessary, okay? The 8th term is 1 over 5,040. Is that enough so that the estimate is of our series, of our sum, is correct to within 3 decimal places? Okay, well, if they, you know, if you were then, you know, that what, I'm not saying this the right way. We're trying to, again, figure out how many terms of the series we need to add so that our partial sum is correct to 3 decimal places. So what if you added the first 7 terms of the series? They call it S sub 6. I want to call it S sub 7. If you added the first 7 terms of the series, you're going to get approximately 0.368056. Does that approximate the infinite series, the sum of the infinite series, correct to 3 decimal places? Well, by using the alternating series estimation theorem, we can say then we can say that the absolute value of the sum of the infinite series S minus the partial sum S sub 7, that's the sum of the first 7 terms, that would have to be less than or equal to B sub 8. Okay, now B sub 8, I can take this part out. It's just kind of confusing that B sub 8 is equal to 1 over 5040, right? Let me try to write it in there. Okay, 1 over 5040 is B sub 8. But that is going to be less than 5 over 10 to the 4th. Remember, we are trying to get our estimate to correct to within 3 decimal places. So that means that you're bound on your error. You would have 5 on top, and then on the bottom you would have 10 to the 3 plus 1 power, which is 10 to the 4th power. 5 over 10 to the 4th power is 0.0005, and that is, let me see here. I want to be careful here. Is that less than? Yeah. 1 over 5040. 1 over 5040 here. Okay, 1 over 5040 is less than 5 over 10 to the 4th power. So because of that, then adding the first 7 terms of the series will give us an estimate to the sum of the infinite series correct to 3 decimal places. Okay. So, effectively then, the difference here between the sum of the series and the partial sum of the first 7 terms of the series is less than 5/10,000ths. Hence, the partial sum of the first 7 terms of the series approximates the sum of the series correct to 3 decimal places. Okay? Does that make sense? All right. Are there any questions on that? Okay. How many feel reasonably comfortable? Are there any questions? So you see, like, what you could do is if you were trying to approximate the sum of your series to correct within, say, well, that's a good question, Michael. How do you know? Well, yeah, it's trial and error, Michael. You have to keep adding terms of the series until you reach a term that's smaller than your threshold. In this case, the threshold was 0.00. Well, in this case, the threshold was 5/10,000ths. So it's trial and error. But the homework problems will be reasonable in terms of, how many terms you have to go out in the series. And of course, in real life, right? I mean, if you were trying to approximate the sum of the series and say to correct to within, say, maybe in an astronomy application, maybe correct to within 20 decimal places, you could write a program that will keep doing that until a condition's met. How many have heard of like an if-then statement? An if-then statement in programming. Yeah, you could say, you know, keep adding. There you go. A lot of you have. Keep adding terms to the series, but if the next term of the series is less than, you know, 5 over 10 to the 20th power, then, or I should say 5 over 10 to the 21st power, if I want correct to 20 decimal places. If my next term of the series is less than 5 over 10 to the 21st power, you know, and the loop. So, all right. Well, if there are no questions, I'll stop the recording here.